All right, last example. This one, little warning, is going to involve some trig, and for this reason often throws people off the first time they see it. So, a plane flies 3 miles in altitude above a radar station at 5 miles per second, pretty fast. How fast is the angle between the radar station, the plane, and the ground changing 3 seconds after it passes directly overhead? So, take a second, see if you can figure this out, get as far as you can, and then maybe restart the video. But I'm going to go ahead and chug right along. Hopefully you gave this a try. For a lot of people, the hardest part is just getting started in drawing this thing. So here's the ground. Let's draw ourselves a little radar station. And a plane. Childhood Austin had lots of practice drawing planes. They would usually look kind of silly. Like this. There's my plane. Person goes in there. Some speed lines. Great. Maybe narrow that up a little bit there. There we go. Okay, so something like this is happening, and it's maybe worth thinking about what is the underlying shape we care about. So we care about an angle in between the ground, the plane, and the radar station. So this radar station is pinging, boop, 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 that plane, and there is some angle, theta, right there, which hopefully to you suggests that we care very much about completing this triangle. Right, that triangle right there, which is in fact a right triangle. Once you realize we're dealing with that angle and that triangle, then sometimes people start to have some success. So if you were having trouble just getting that far, pause the video. Try to move forward again. I'm going to keep on going and try to start labeling these things. So one of the sides of this triangle is constant, so we can go ahead and label that thing. Let's do it. Looks like it is 3 miles in altitude. Okay. And from there, everything else is changing, right? The length along the bottom here is changing. This angle is changing. So we should probably start working on this, what were we given and what do we want phase of things. So we were given a rate. That rate is that I am flying at 5 miles per second. And so I need a variable here. Let's just call this x. X makes a lot of sense. If you want to call it b or whatever other letter you want, that's great. But in this case, dx dt is equal to 5. And we want something else. We want, well, I've already labeled it, so I'm going to call this d theta, fix that theta there, d theta dt. How fast is that angle changing? And we want this at a certain time, which is when or rather after 3 seconds. Okay, so there's a good chance that you are going to take that and you're just going to run with it, and then afterwards you realize it's pretty hard to plug seconds into this picture, right? Seconds doesn't exist in the variables I have so far. I mean, if I try to start labeling variables, I would say, oh yeah, so x is distance from that radar station, by the way, along the ground. Theta is that angle, and t is of course time. And so these are my variables. But I don't really see, I don't know if I want to plug in s for seconds into time. Usually it doesn't work very well. You may or may not see this ahead of time, but let's go ahead and calculate this. How far, what is x after 3 seconds, right? And this is going to help us out later. There's no reason why you couldn't figure this out later and then solve it, but this is actually when x is equal to, do a little math here, 5 miles per second times 3 seconds is equal to 15. And you can check the units on that too, right? If you're a units person, as everyone should be, 5 miles per second times 3 seconds equals 15 miles. I guess I shouldn't write. Here you go. Yeah, so it works out. So a little bit of work now will save us time later. Again, if you don't see all of this right away, no reason why you can't kind of work forward and backwards. Okay, what is the relationship here? What relationship am I working with? Do you see it? I hope you do. You have a right triangle with some angles. And I already warned you there was some trig involved. So it's tempting to try to do like a Pythagoras here, but we really don't care about that diagonal length. What we care about is the angle, and the relationship I have between the angle and those two sides is tangent of theta. Oh yeah, do you know? Opposite over adjacent, so 3 over x. That's it. Tangent of theta is 3 over x. And this shows up more than you'd think, these trigonometric relationships. All right, let's go ahead and implicitly differentiate that. Now, if you hadn't gotten this far on your own, pause the video. See if you can pick it up from here. But I'm going to go ahead and do it. Looks like I get a secant squared of theta, d theta dt is equal to, if you don't know this off the top of your head, let's rewrite it up here real quick. This is 3 times x to the negative 1. So negative 3 x to the negative 2. Okay, also known as negative 3 over x squared. By the way, tempting here to forget that I need to do the chain rule on x. I have forgotten this many times myself. So this is dx dt. Okay. One of the dangers of using x as a variable is that it's easy to forget when I'm doing implicit differentiation with respect to t. All right, now we'd like to plug some things in. So we know quite a bit of this. We want to know what d theta dt is. We know what the x value is. So my x value, we already found out was 15. If you didn't figure that out beforehand, this would be your big clue, right? This would be your, oh my gosh, look, I need to plug in an x and I don't know what it is, and that'd be your clue. I need to solve for what is x at that point in time. Okay. I know what dx dt is. That is given. That was a 5. But I've got this secant squared theta business that I need to worry about. So let's do a little bit of side work to figure out what this is. There is kind of a pretty way to do this and an ugly way to do this. The ugly way to do this is going to involve something like an inverse tangent. So please don't do this, but someone might try. Theta is equal to inverse tangent of 3 over x. And then you could try to plug this in and say theta is equal to inverse tangent of 3 over 15. And you could then plug that in to secant squared. If you do it right, you'll get the same answer. It's not very elegant though, and there's probably going to be a lot of rounding errors along the way depending on how you do this. The beautiful way to do this, and believe it or not, we do pursue beauty in math, is like so. Let's take our triangle. We know this is a 3. We know that at this particular theta, whatever it is, along the bottom I have a 15. And now I want to know what is secant on this triangle. Well, secant is 1 over cosine. So this is also equal to, cosine is adjacent over hypotenuse. This is hypotenuse over adjacent. Okay, so I need to know the hypotenuse to figure out the secant squared, but luckily I know my right triangles. I know that a squared plus b squared is c squared. So this is the square root of 3 squared plus 15 squared. Okay, so that means that secant of theta is equal to, well, hypotenuse over adjacent, the square root of 3 squared is 9, 15 squared is 225, so 234, hopefully I did that right, over adjacent is 15. Great. So rather than solving for theta and plugging in, we can actually just solve for secant. All right, well, we really want is secant squared anyway, so let's go ahead and go back over here. Secant squared is going to be, looks like 234 over 15 squared, and that d theta dt comes around. Okay, so that took a little while because I solved it two different ways, but in general, this thing on the right is called a reference triangle. And whenever you find yourself in a position where you're trying to plug like an inverse trig function into a trig function, it's probably a sign you should just go back to the original triangle and figure out on that triangle what is this relationship. From here, we can go ahead and clean this thing up. We can solve for d theta dt. So d theta dt is equal to, if I multiply both sides by this 15 squared, boop, it's going to cross out with this 15 to the negative 2. And what's left is just, looks like I have a negative 15 over 234. Beautiful. Normally I'd say, hey, make sure this fits your intuition. It's negative because that angle is decreasing. So that's good, right? As the plane goes forward, this angle gets smaller, so negative makes sense. Beyond that, this thing is in radians. It's a little bit tough to have a good intuition for, is this a reasonable number? So at least checking the sign is good. All right, go back through that one. There's a lot of good stuff in there, as well as our old friend trigonometry. Hopefully this is a challenge, but hopefully it's interesting and fun after a while too. All right, I'll catch you all in the next lesson.